Okay, we're going to take a look at a weird relationship here, and at first it's not going to seem like it has anything to do with the good old Taylor polynomial magic formula stuff. But between today and tomorrow, or this lesson and the next lesson, you're going to realize that this concept that we're about to do is deeply entwined with the magic formula. And for today, we're just going to say, hey, you see this rational function? You may not even know what that is. Let's make a geometric series out of it. Here's what I mean by that. In this problem that you're looking at right there, ignore all the mumble jumble for a second. We have a rational function. It's 1 over 2 minus x. It's a rational function because it's written like a fraction or a ratio. And we're going to take that thing and we're going to turn it into a geometric series. Kind of a weird concept. So our rational function via algebra trickery gets converted into a geometric series. So here's what your brain would say. I know this is the formula for the sum of a geometric series. Well, if I can use algebra trickery to start making this look more like that, life is better off. I see there's a 1 there and there's a 2 here. So what if I divide by 2, divide by 2, and divide by 2? That's basically saying I divide the bottom by 2 and the top by 2. So there it is in writing. And when I do that, holy moly, I simplify and I have a1 minus r. R is your common ratio, which shows up there in a geometric series. And this is your first term of the series, and as long as we're starting at n equals 0, the coefficient is that. That wouldn't be the case if we weren't starting at n equals 0. But anyway, through some algebra trickery, this rational function becomes this geometric series. And the reason why this works is this. This, for certain values of x, this series would sum up to or equal a specific value. The specific value that it would sum up to is the same thing or could be calculated via this formula. So if this is roughly equivalent to this for certain values of x, then converting this into this leads to converting this into this into this. So that's why the math works out. Or you could just say, hey, the teacher told me to take this rational function and turn it into a geometric function, so like a good soldier, I did. On this next example, we're going to show you some algebra trickery to add to your algebra trickery. This rational function looks almost exactly like that, but it has a plus instead of a subtract. Okay, well, I still know I want to think about this, a over 1 minus r, and this is a very good place to always start. So if I divide everything by 2, I get a1 minus r. Oh, wait a second, that's not subtraction. But a clever little trick, if I make that subtraction, and then I just assign a negative sign to that, minus a minus is a plus. So this was a tricky way to get a subtraction there so I could match up the 1 minus r. Now if I take this, as long as I'm starting at n equals 0, this is my coefficient, this is my common ratio, this geometric series is equivalent to that rational function. All right, let's add another layer of spiciness. This is a rational function. We want to write the geometric series, but now we want it centered at x equals negative 2. We didn't mention a center with these first two problems, but we ended up with a geometric function centered at x equals 0 because in each case where you see that x, you could have written an x minus 0 to the n power. And that means centered at x equals 0. And you'd never do that because that just seems weird, so you write it that way. Well, we've got a different situation brewing in this latest problem. If I want to center this at x equals negative 2, then I'm going to have to play around a little bit with this x. So I'm going to show you what I'm thinking. Centered at x equals negative 2 is really x plus 2 because it's x minus the center. The center is negative 2, minus a minus 2 is a plus 2. So as soon as I see this information, I convert that into that. But I need to make this thing equivalent to that. So instead of saying 6 minus x, I have, I don't know, minus x plus 2. I just have to figure out what is the I don't know that makes this entire denominator still equivalent to that entire denominator. You could probably get that done by a little bit of intelligent trial and error. And in this case, it ends up being an 8. And if I go ahead and distribute 8 minus x minus 2 is really a 6 minus x, which is what I have there. So I feel comfortable converting this into that. And I unveil the next step. Usually I say I want to concentrate on making this become a 1, so I divide by 8, divide the entire denominator by 8, and the entire numerator by 8. I get that big honkin' mess, but I can make that look a little bit better, do a little bit of reducing. A, 1 minus r. This is a pretty clunky r, or common ratio, but it's legal. So there's my first term, and there's my common ratio. So this is this, centered at x equals negative 2. We're going to move on to one last final thing, but so far, just to recapture, you should feel comfortable knowing that you can take a rational function and via algebra trickery convert it into a geometric series. The last thing we're going to do is just going to be a reminder, but you'll eventually see, for a good reason, a reminder that this series is convergent for some x values and divergent for some x values. So we take the same rational function we've been working with the same center, and just say, hey, find the interval of convergence of that thing. I know this is old news to you, just a reminder. We took the rational function. In the previous example, we did the hard work to convert it to geometric. What's the interval of convergence there? This would be my thought process. I would say, hey, that thing's convergent when the common ratio is less than 1. Technically, the absolute value of the common ratio is less than 1. So when this is less than 1, I have convergence. So I go ahead and just do the algebra. You see the algebra right there, and I end up with an interval of convergence. And I don't have to check these endpoints because I know in a geometric series I always have soft endpoints. If you feel like checking them, go ahead and take those endpoints, plug them back into the original series, and see if it's convergent or divergent. The reason we did this quick review of interval of convergence will become apparent in the next couple of lessons. All right, that's the show for this one.